Okay, I feel like I need to not use these markers, but we're going to do them anyways. And I'm going to change y'all's view. So, pretty sure it's already recording. What we're going to do today is half of 4.4, which is going to be solving exponential and log equations. So you should be able to get through like half of your 4.4 homework after today, y'all. Okay. So it's 4.4. It's solving exponential and log equations. Okay, so technically I have two different methods here that I'm going to show you. The first method is going to be we make the bases, right, on both sides of the equal sign equal to each other. And then when you do that, in a way you can kind of cancel them and you just have the exponents equal to each other. I think it's the easier way, but if you can't use that way, then what we're going to do is take the log of both sides. So method one is when you have it in this exponential form, and what we're going to do is make bases equal, then set exponents equal. I'll go ahead and say to each other. And so what I mean by like making the bases equal to each other, say we have 25, but what we need to do is we need to write this as a base of 5. So wouldn't I just write that as 5 squared, right? Got the number 25, but in order to make my bases the same, I need this base to be 5. Well, 5 squared is 25, so those are equivalent, right? If we have 16 on one side of the equal sign, but we needed to make our base 4, well, then I could just rewrite that as 4 squared, correct? If I needed to make my base 2, I can make it 2 to the 4th, and this is because 4 squared is 16. 2 times 2 times 2 times 2 is also 16, okay? I did a couple of different examples here. Say we have 64. If we needed a base of 4, 4 cubed is 64. I could also be written as 2 to the 6th. And then if we have 1 over 8, but I needed to write that, right, in order to get my bases the same, I needed to write it with a base of 2. Well, I know that since this is a fraction, if I'm going into a whole number, what would happen would be my exponent would be negative, right? These are equivalent. I actually get here from here, but if I see this and I need a base of 2, I would write it like this. And then lastly, say I have like 1/3, that would come from 3 to the negative 1. So if you see a fraction, but you actually need a base of 3, I'm just showing you how like these are all equivalent, right? Okay, let's see if I can write it a different color on this blue. It just feels like there's been a bunch of black marker everywhere. Okay, so let's look at this example right here. Say we have 2 to the, and in our exponent, we have 3x minus 8, and then we have equal 16. This is an equation, and it's in exponential form, right? That's my b, that's my base. This is my x, this is my a. This is exponential form. If it actually wants me to solve for x, the only way I know how to do that is to make the bases equal to each other, and then set the exponents equal. When we make the bases equal to each other, it's like they just kind of go away, but they have to be set equal first. So I notice here, I don't really have a way to write 2 to where it's going to give me 16, right? Like I'm not going to make that base go up. But if I look at my 16, I can write 16 as 2 to the 4th. And now I have 2's for both sides of my bases. So that's what I would want to do. Got 2 to the 3 minus 8 equals 2 to the 4th, right? Because 2 to the 4th is 16. Now on both sides, I have the same base. Technically, they're going to go away. And all I have is just 3x minus 8 equals 4. Do you see how now that's just like a normal equation that we've solved many times? So we just solve for what our x is. So I would move my 8 over, right? And I would get 3x equals 12. And then divide, I would get x equals 4. And then like if you did want to check yourself, 3 times 4 is 12, minus 8 would be 4, and 2 to the 4th would equal 16. Okay. Usually you can just kind of look and see like, wow, that answer's pretty insane. I don't think it's going to work. But going back and plugging it in, I do see that 4 is what my x is. Okay, so let's do this one. Say we have 5 to the... In my exponent, I've got 3x minus 6, and then equal 125. So knowing I need to get these in the same base, this is a 5. I know I can write 5 to the something and also equal 125. And that would be 5 cubed, right? So I've got 5 to the 3 minus 6 equals 5 cubed. Bases are the same. So now all I've got to do is just set my exponents equal to each other and solve for my x. Here what I would do is move my 6. So it would actually be 3x equals 9, and then x equals 3. And just really quick, if you went back, 3 times 3 is 9. Minus 6 would give me 3, and 5 cubed is 125, right? Okay, I've got 2 more examples for this. Okay, say we have 27x plus 3, that's my exponent. 27 to the x plus 3 equals 9 to the x minus 1. So, right, if I'm looking here, I know that I have a 9. I've been using the smaller number, right? So it's like, okay, so I want to write this with a base of 9, but 9 to the first power, squared, cubed, anything, I'm not getting to 27, right? So instead I need to see if there's a common base that I can write both of them as. I know that 9 can be written as 3 squared, right? And I know that 27 is 3 cubed. So that's what I use as my base. The only thing is what's different here is I have 3 cubed goes up in the exponent. It needs to multiply what was in the original exponent. And then over here, I would have 3 and then squared open x minus 1. Do you see that? Okay. And that was literally just because if you try 9 squared is 81. Like I'm already past 27. So I need to see, can I write both of them as a different base? And so now that my bases are the same, just set your exponents equal to each other and solve for x. So we would have 3 open x plus 3 close equals 2 open x minus 1 close. And then y'all, that's just like distribution, right? That's something touching the parentheses. Let's go ahead and distribute that in. I get 3x plus 9 equals 2x and then a minus 2. And now what we do is we just solve this equation right here. I would move my 2x from the right-hand side to the left-hand side, and I would move my 9 also, right, to the right. So let me go and do that. This becomes just x plus 9 equals a negative 2. And then now move your 9. I get x equals a negative 11. They'll, of course, throw problems in there that look really scary. As long as you understand the exponent rules and can refer to them, you should see how you can change the base. And then that way you just go ahead and cancel them. Okay. Okay, let's do this fourth problem. Okay, I have 5 and it's raised to the 2 minus x power. And I have equal 1 over 125. So notice that smallest number on the left-hand side, that's a 5, right? Like ideally, I can write the right-hand side also with the base of 5. I know that if I do 5 cubed, right? I know that 5 cubed equals 125. But I don't need this whole number 125. I need it to end up being a fraction. And the only way that I'm going to have something raised to an exponent and then the answer be a fraction is if my exponent is negative, right? Because 5 to the negative 3 would be 1 over 5 cubed, which is 1 over 125. Does that make sense? That's just knowing that exponent rule and knowing what's going to get me to here. And so this right here, 5 to the negative 1, why did I say 1? 5 to the negative 3 is going to be what this changes into. So I have 5, 2 minus x equals 5 to the negative 3. The whole reason why I'm even doing this is so that my bases are the same, and now all I have to do is just set my exponents equal to each other. Why did I do 2x? When 2 minus x equals, the exponent here is a negative 3. Then if I move that 2 over, it's a positive 2, so I would do a negative 2, and what you do to one side, you have to do to the other. Those cancel, which is great. What I have left on the left-hand side is a negative x. On the right-hand side, those signs are the same, so you would add them and keep their sign. And in even a simple equation, you never care what the value of a negative x is, right? We want the value of a positive x. So technically, you would just divide both sides by negative 1, or you could just remember, just change the signs of the left and the right. Because if I divide this by a negative 1, I get a positive x. If I divide this by a negative 1, I get a positive 5, right? So that would be your answer. And literally, if you kind of look back up here, like, hey, I'm just going to check myself and make sure 2 minus 5 signs are different. I would subtract and get 3. Keep the sign of the larger, I get a negative 3. And 5 to the negative 3rd power is this. Does that make sense? Okay. So that's how you do those. Now let's do this second method, which you notice that the problems look different. And yellow paper. So this is the second method. What you do is you take log of both sides. Okay, so our first example is 4 to the x equals 15. So the reason why I know to take the log of both sides is because if I look at this, I know that 4 could be written as 2 squared, right? Like that's really it. 4 to the first power, of course, but then it looks like you got 2 squared. And then as far as 15, like I don't have a base that I could raise to an exponent to equal 15. So the ability to change their bases to be able to just set the exponents equal to each other, like that fails me here, right? So what I do instead is I'm literally going to take, I'm going to take the log of both sides. I know that what I want to do is solve for my x. And so for this problem, what we do is we're going to take log base 4 of 4 to the x equals, and then log base 4 of 15. And this is because I'm just understanding that if I use this property here, because it's in that 3-step form, 4 to the x, don't I just get x? And so now on the left-hand side, I have x equals, and then I'll have this right here. And that's using that property. So x equals log base 4 of 15. And y'all, that's because I used the property that says log base b of b to the x is just x. And I want to solve for x. So that was kind of sheer manipulation on my part, knowing that I want to solve for x. How can I get x on that left-hand side? So once it's in terms of log, what we can do is this would be the change of base formula, right? Because this is saying 4 to the what power equals 15. That's going to end up being a decimal, and it's not something that we're going to easily be able to solve. But because I know I actually want a value for my x, this is when you take the log of the big over the log of the little, and you just enter this into your calculator, and you're going to get an approximate answer. And that's actually going to be the decimal approximation that if 4 is raised to it, you'll end up getting your 15. Oh, I don't even have my calculator with me. I have the answer in front of me, but in here we can actually see my calculator. So let me get it. This thing's loud. Okay. So I'm doing the log of my big number and then divided by the log of my little number. And so I just get log 15. I'm going to close it. And then I'm going to divide it by log of 4. And what I get is 1.953445298. We round to the third decimal in all of these problems we're fixing to do. And in your homework, it would tell you what to round it to. So this is approximately 1.953. Point 953445298. If you just weren't sure, did I even input this into my calculator correctly? I remembered big and little, but I just don't know. The answer that I got was 1.953445298. I literally just rose 4 to that decimal, and what I get as an answer is 15. So if you're checking yourself here and you don't get what your A is, which would be the answer, then that's how you can tell, okay, maybe I didn't input it correctly. Huh? Does it matter whether you use 15 or 4 to check it? You would have to use 4 to check it, because the answer here is the exponent on your 4. Because this is the logarithm form, right? Which is x equals log base b of a. And in exponential form, you have b to the x equals a. So what I would be doing is the answer that I got is x equals 1.95, that whole decimal, right? If I wanted to check it, my b would need to be raised to my exponent, and here my b is 4. Okay. So like you actually couldn't, if you rose 15 to that, you definitely won't get 4. You know what I mean? You have to like kind of see it in that exponential form. Okay. So let's do the second example. This one is 10 to the x equals 120,000. This is saying 10 to what power equals 120,000. I know that I don't have an exponent just right off the top of my head that I could raise this to equal this. And I know that I don't have a base to where I could have these equal, right? So that's when it's like, okay, instead what I need to do is take the log of both sides. Here, I took log base 4 because I knew what I wanted on my left-hand side was just my x. So I was like purposefully using that property, right? And then for problem 2, because this is a 10, if I use the common log, right, because that's log base 10, then I'll have the 10 to the 10 to the x. And in a way, it's like I just now made it to where all I have is x. So log, you can write it or not write it. I think here, kind of solving it and seeing it, you'll see that property a little bit better if you actually do write that base. And then, you know, similar to the majority of the equations, what you do to one side, you have to do to the other. So I'm going to also take log base 10 of 120,000. And then noticing, sorry, because I skipped a step here. I hate it when I do that. Noticing that right here, I have a property that states if you have b to the b to the x, the answer is just x. Here, that's my answer. It's just x equals. And then we have log base 10 of 120. So you literally, right? The other one, there was, sorry, I'm trying to point it out right here. This one ended up being a change of base. You took this divided by this. This one right here, you can just enter it into your calculator. If you divided it by log 10, I'll go and show y'all. But if you do log 10, that's just 1, right? Because my base is 10 and 10 raised to the first power is 10. So dividing this by log base 10, you're just dividing it by 1. Like it won't change anything if you kind of keep doing the same steps. But if you just enter this one in, you get 5.0718. We're just going to round it to, it's approximately 5.079. Okay. Got 2 more of these, y'all. Okay, so say we have 10 to the x power, and then the same size as 10, subtract 5 from it, and then set it equal to 32. You're just going to look at this the same way you would another equation, right? Like if I'm going to try to solve for my x, in a way I want to like isolate that variable. And right now I've got a term that has that variable as an exponent, and then I just have like a -5. So we're actually going to add 5 to both sides. And we get 10 to the x equals 37. And then right here, I know, right, if this is 10, I could write it as 2. I know I can't even, I was about to say 2 to the something power. I can't write it as a base of 2. I can't write it as a base of 3. I can't do that, and I can't do anything here. So that's how I know to go and take the log. Because it's 10, I'm going to take the common log of both sides, so that I have log base 10 of x. There's that property. And then what you do to one side, you have to do to the other. So on the left-hand side, right, b to the b to the x is just x. So you have x equals log base 10 of 37. Because it's log base 10 of 37, I don't have to do the change of form. When it was log base 4 of 15, I needed to do the change of form because I don't have a base in here that's 4, right? But I do have log base 10 by just hitting the log button. So log base 10 of 37, you just type log 37, enter, there's your answer. It's 1.568, rounding it to the third decimal place. Does that make sense? Why did the change of base on that other one and then now I'm not doing it here? Okay. Let's do this problem. This is 4. And then we have Euler's number. We have the E raised to the 2x power. And then we put equal to 40. Again, that same train of thought, solving an equation, need to isolate the variable. I noticed that I've got this coefficient multiplying my E, right? So what I'm going to do is I'm actually going to divide both sides by 4, and I would get E to the 2x equals 10. And now that I don't have a coefficient right there on my E, what I can do, because I know that the inverse here in order to solve this equation would be to use that same property. And because my base here is E, I'm going to take the natural log of E, right? If I got a base of E, I wouldn't take log because that's base 10, right? But E also be written as natural log base E. And doing this, do you see how now there's that property? Got b to the x. So it's just this right here. It's just the exponent that remains. So it's just 2x equals natural log base E of 10. I'm solving for x, right? I've got a 2x. So the opposite, right? The inverse of that multiplication would be division. I'm literally going to divide both sides by 2. And what I get, I'm going to come right here, y'all. What I get is x equals natural log base E of 10 divided by 2. This is what I'm going to enter into my calculator. See it? Okay, so my natural log button is right here. It's the ln. And then, of course, that E, that's already the base, right? You don't enter anything here. Okay, I can use my natural log button because I know it's base E, and this problem is base E. I do enter my 10 and I close it. If you don't close it and you just do the division symbol and then 2, it's actually going to do 10 minus 2, and now you're taking the natural log of 5. Do you see what I'm saying? So make sure you close it so you separate numerator and denominator. Then divided by the number 2, I get 1.15129. Rounding it, we're going to get 1.151. This is saying that my x is approximately 1.151. That make sense, y'all? Yeah? Okay. So I'm going to go ahead and show you your quiz. It's one doing it where you make sure the bases are the same, and then it's one doing it like what we just did right here. Okay, and then so just piece of paper, your name, today's date. And remember, this counts as your attendance. I don't know if people know that. I think I remember seeing some people, but I don't have a quiz for you. So like you weren't really counted as being here. There's just 2 problems. When you're done, you're free to go. Merp. And I'm gonna zoom in a little bit for y'all. Yes, Madison.
paper that you did the second one, I think.
The paper that I did what?
Method 1, problem 2.
Yes. Hold on 1 second. Method 1, that's method 2. Should be on blue paper. Oh my goodness. Here we go. Last page. That one right there?
Yeah.
You're welcome. If y'all can't see that, make sure you tell me. I know writing in pencil, sometimes it's not super clear.